Problem number 4, I think it was. Rafael, welcome. Hello again. Good to see you. All right, so let's see. Did I set this to present for me? All right. And then if you have a question, just jump into the chat box or turn your mic on and ask. All right, new page. Oh, I think I can probably turn off my phone. I don't think anyone's going to call me for class. Screenshots. So our goal today is to just play more with limits based on the stuff in section 2. And we've gotten through about half to 2/3 of that over the last couple of days. All right, so this is a problem, again, where we're trying to take secant lines, which is a line through 2 points on the curve, and see if we can let the 2 points merge onto each other and turn it into a tangent line. So we'll take a look at this graphically, and we'll take a look at it numerically. So some app like Desmos or TI calculator would be an excellent thing to have out right now. So I'm going to get Desmos to help me out here. Desmos graphing calculator. Oh, let's see. Oh, do I have it on this one? Let's see. Hang on a second. I got to show you guys some cute math if I can find it. So here, Des. I think this is the one. Somebody with way too much free time on their hand made like 100 different curves, and when you put them together, you get Superman. So if you're bored this weekend and you're done with your calculus homework, feel free to make a cute sketch in Desmos. A friend sent that to me a while back. See all the functions he used down here to make that happen?
Impressive.
Isn't it?
Yeah.
Man, this person needs a life. Crazy. All right, back to real math. Desmos. All right, so square root of x, then plus 5. So highly recommend when you're using Desmos, use function notation. So give it a name. We beat the heck out of f of x, but we can call it anything we want. Since it's a square root, I'm going to call it s of x. So I just need to remember to refer to it later with the right letter. And SQRT, oops, I forget that type equals, it's how you get the square root symbol. It's kind of the universal.
I just hit the little,
There's a little
bottom.
Where? Right here?
Yeah.
Oh, I forgot about that. Yeah, or you could just hit the square root button down there. They have a whole bunch of other functions at your disposal, like the inverse tangents and stuff. Okay, cool. I forgot that was there. Thank you, Sarah, for reminding me. Okay, so we want x, and then I have to arrow outside of the root to get the plus 5. If I forget to do that, I'm going to get the totally wrong function, right? If I accidentally put the plus 5 inside, that's the wrong guy. Plus 5. Okay, so there's my function. X value I'm concerned about is 4. They claim the y value is 7. Some of the problems I gave you like this didn't give you the y value. You had to go find it. So I'm just going to go find the points. 4, comma, what's my function called again? S. So I would do S of 4 to get the y value.
Hey, Mr. Parker, none of the online students have any audio.
Oh, somehow I hit mute. Is it back?
Do not.
No? Yes?
Yeah, you're back.
I'm back. I hit mute somehow. Shit.
How long have they not had audio?
How long have you not had audio?
Not that long, but
Sorry. Man, I owe you guys some pizza. Do you want me to go back and look at anything here? Or is that, so here I was doing synthetic division to double check that limit.
yeah, I got it all down. So
I think I was tracking all right with that one.
Tracking all right on that one. All right. Okay, so Sam, it's your job to remind me to check the chat box once in a while.
Okay.
That's usually if we're sitting in the front. This is why you never sit right in front of the teacher.
Sarah, can you remind him to help him
Yeah, I
check
got
the
you.
chat box there? All right. Sorry. Okay, so that's going to be a weird recording later. Okay, so sine of x over x is what we're looking at now, and in Desmos, we were trying to get close to what's happening there, and we zoomed in on it too, and one feels pretty good there. So we've got this thing is equal to 1, and what we're going to find is as we work with limits, it's going to be good to have these limits that we kind of memorize, like, oh yeah, I remember that one, that goes to 1, or that one goes to pi, or that one goes to e. And we're going to use those facts later rather than recreate them each time. So this is a super important one. Write it down, put stars and smiley faces all around it. It's super important.
Well, it's also a maximum.
What's that?
It's also a max
It's
point.
also a maximum, yeah. And the interesting thing here is that although the limit is 1, f of 0 does not exist. So it's this thing we get to approach, but we can never touch it. It is just not there. It's this hole in space and time. All right, so check this out. We're going to do a slightly different version of that. What happens if instead we take the limit as x approaches 0 of the sine of 3x divided by 3x? So graph it, see what you see, and then I'll show you a cute little bit of algebra with limits. That's kind of fun.
It looks like the same thing.
Yeah, so it's got a different shape. So I'm going to go back to the home screen here and just change those labels again. Let's go from -1 to, actually, let's go from 3 to 3. Yeah, and then I'm going to call a new function g of x. G of x is going to be equal to the sine of 3x over 3x. Okay. So it's a slightly different curve, but it's kind of the same, right? It's just squished is all. It's just a horizontal compression on that graph right there. But it looks like it has the same limit at 0, doesn't it? Yeah, and if I replace the 3x with a 5x, it would still look the same, it's just more squishy. So it's just a variation of it. So graphically, we're looking at this thing and saying, yeah, that again looks like 1 to us. And we could check a few values and say, yeah, it's heading toward 1. So here's my note. I'm going to combine this with another limit. Suppose I took the limit as x approaches 0, equal sign of 3x. What is 3x doing as x goes to 0? It's going to go to 0, right? We can just plug in 0 and we can see that. If you consider the graph of y equals 3x, it looks kind of like that. It has the point 0, 0. So this one's pretty easy. It's a linear function. Nothing weird's going on. It's just 0. Okay. So what I'm going to do is I'm just going to throw in a little substitution here. I'm going to let u equal 3x for a minute. And again, my claim is that if I look at the limit as u goes to 0 of u, well, it is 0, right? That's basically just this statement with u's in it instead. So up here, if I make that similar substitution and I replace the 3x's, I just have the limit as u goes to 0 of the sine of, oops, back up here. The sine of u over u. So the bottom line, as long as this thing matches that thing, I'm good. Yeah. So if from now on you see anything that looks like the sine of x over x, you're thinking, I got this, I've done this one before. So I'm going to give you another variation of this. Oops.
So they cancel out, so they can cancel out.
What's that?
So they use cancel out.
No! There's no cancellation happening here. So the u's do not cancel. This is not equal to sin, because sin on its own means nothing. It's got to have a variable. These things are inseparable. Okay. What's happening graphically is that as these two things head to 0, the whole fraction is getting closer to 1, but nothing can be canceled there. There is no cancellation. Okay, because that's a function. So that would be a lot like saying, take some function f of x and divide it by x, and it's going to be equal to f, right? That the functions don't work that way. So the sign's the same thing. All right, so let's look at the limit as x goes to 0 of the sine of 5x over x. Uh-oh, slight problem here. Yeah, there's no 5 in the bottom here, right, to match it. So how can I relate this back to the function I know, which is x over x, or u over u?
It's 5.
You think it's going to be 5? Okay, so graph it and check. And then I'll show you a cute bit of algebra that can help us do that. So I replace the 3 with a 5, and I get rid of the 3 out of the bottom. And, ooh, it's way up there. Hey, Rob's right, it's 5. Okay, so here's why. Great. According to I know for a fact, based on, well, I know by experimentation, that let's make that a u, if I take the sine of something over that same exact thing, the answer's 1. This is an established thing we have now. This is just missing, these guys don't match. Well, couldn't I just put a 5 in the bottom there? Sort of, but that's now a different function than what I started with. So I have to compensate by multiplying a 5 into the top. Yeah. And it turns out that that 5 in the top, I can just kind of pull it out of this and say that's the same thing as 5 times the limit as x goes to 0 of the sine of 5x over 5x. So here I've got a 5 in the numerator, here I have a 5 in the denominator. 5 divided by 5 is what? 1. So I'm not hurting this thing in any way, but now I know what that thing's equal to. What's that thing equal to in the box?
1.
It's 1, but now it's 1 times 5. So there's the limit 5. And that's a trick we're going to pull a lot by just messing with limits we already know in ways like this. A lot of tricks. Okay, that was fun and exciting. Let's do another fun and exciting one. Check out the limit. Let's write the blue. The limit as x approaches 4 of the square root of x minus 2 over x minus 4. Plug that into your calculators. So Desmos that sucker, or TI, whatever your favorite utility is. So let's give it a name. Equals fraction QRT of x minus 2 and over x minus 4. That's a cute function. All right, so there it is right there. And at x equals 4, it looks like it's all right. Check it out. F of 4 is, oh, there's a hole there. Darn it. But we think there's going to be an answer. So we just got to play around and see what it is. So let's just get close to it. F of 3.999 maybe. One side, on the other side, F of 4.001, 2.5002-ish, 2.4998-ish. What's right in the middle of those two numbers? 0.25. I said that wrong again. Man, where's my decimal point issue today? I'm going to rewire something tonight. Okay. 0.25002, 0.24998. Right in the middle is 0.25. So I think to fill that hole, I just need to plot the point 4, comma 1/4 or 0.25, and there I filled in the hole. So that must be the limit. So we think this limit here is 0.25. All right, so let's play with that idea a little bit. Actually, we can apply some algebra to this. There's two ways to do it. You have an idea? Okay. Rob's shaking his head. Tyler?
Maybe the weak factor equal to 1.
What's that?
Multiply equals 4, and
So that becomes a 1.
then
Okay, so if I multiply by 4, I would have 4 times this limit. X goes to 4. Square root of x minus 2 over x minus 4 equals 1. Yeah, that's a true statement if the top statement is true. So how does this 4 help me here? Can you do what? Divide? Can you take x minus 4 into the square root of x minus 2? Sure. It's a little tricky, but you could do that. Another idea?
factor the x minus 4 into square root of x minus 2.
Yeah, there you go. X is equal to the square root of x squared. Right? Square root of x times the square root of x. So that means I can factor this denominator as the difference of two squares. So I'm saying that in the denominator, I have the square root of x squared minus 4. That's the difference of two squares. That means it should be equal to the square root of x minus 2 times the square root of x plus 2. Yeah. And then I'm going to get to cancel a factor. Okay, so I'll write that in a new screen here.
Hold on a sec.
I'm going to rewrite the whole thing in a new screen.
All of that stuff at the bottom too?
I'm going to condense it, yes.
Okay.
Yeah. So what I have now is that the limit as x approaches 4 of square root of x minus 2 over x minus 4 can be rewritten as the limit as x goes to 4 of the square root of x minus 2 over square root of x minus 2 times the square root of x plus 2. And because I found a matching factor, a number divided by itself is 1. 1 times anything is itself. So now, as long as I don't plug in 4 here, I would have a problem. This is equal to the limit as x goes to 4 of 1 over square root of x then plus 2. Kyler, were you about to raise your hand, or are you good? No. Good, okay. And now I'm safe to cheat and plug in. So I'm thinking, question mark, that this is equal to 1 over square root of 4 plus 2. On a good day, square root of 4 is 2. So this is 1 over 2 plus 2, or 1/4, which is that 0.25 we found experimentally. Okay. Now, I mentioned earlier, sometimes there's algebraic tricks to find the answer besides exploring on each side. A limit literally means explore each side. Okay. Here there was a trick. It's just a matter of, can we collect all of these tricks? Is there always a trick? No, sometimes there is. And in most of the problems you're going to get, there's a trick. All right, good on time. Next. Let's look at a problem like Daphne wanted. So we're going to take a look at piecewise functions. You might remember seeing those in your past life. So piecewise just means for part of the domain, we'll use this formula, and for another part of the domain, we'll use that formula. So here is one. Let's let f of x equal x squared if x is less than 2. And if x happens to be greater than or equal to 2, then we'll use x plus 2. So what does this look like? I'm going to graph it by hand and then show you a trick to do it in Desmos. TI can do it too. It's a little trickier trick. So let's see. The dividing line for the domain is x equals 2. So I'm just going to make a little dotted line there. So if that's 1, and that's 2, this is 3, that's 4. I'm going to put a dotted line right through x equals 2. So on one side of the dotted line, it's a parabola. On the other side of the dotted line, it's a straight line. So graphing x squared over here, I get 0, 0. I get 1. Let's put some scale here. 1, 2, 3, 4, 5. Y, x. Back to the left side. 0, 0, 1, 1, 2, 4. And at 2, 4, I'm going to put an open circle because it's not equal to there. And then other side, I guess, these points roughly. So here's the first part of that curve. And it stops right there. It goes to the left forever. Then I pick up with x plus 2. X plus 2, let's use a different color, would normally start right here, and then up 1 over 1, I get a point, up 1 over 1, I get a point. But this says don't start graphing it until you're 2 and beyond. So from here, up 1 over 1, and so that one begins here. I get to fill in that open circle and head that way. So there's that function. So piecewise functions, graphing by hand, basically make a mark anywhere there's a split in the domain. One function gets one side, the other function gets the other side. To tell Desmos to do that for you Desmos users, if you're a TI user, you got to see me before or after class, and I can show you on the TI. Clear, 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 clear. What you do is you start off like normal, but then you put a curly bracket to indicate you're about to give it some more complicated instructions. And then you kind of state it backwards of the way I did here. You state what the restriction is on the domain first. So then I'm going to state x is less than 2.
You're outside your bracket.
Oh, crap. I'm outside my brackets. Thank you. X is less than 2. And then I do a colon. I'll write this on the board too. And then I state, okay, what's the formula? The formula is x squared. And if I zoom out on this, you'll see that it just stops when x is 2. It says, oh, done, can't graph anymore. If you want to continue with other pieces, then you do a comma, and then same idea. What's your condition? X is greater than or equal to, you just type greater than, then equal to, and it throws them together for you. To comma, what's your formula? X plus 2. Oops, what did I do wrong? Oh, a colon, sorry, not a comma, a colon. There we go. And it says, there's your picture. So it's always restriction, comma, restriction colon function, comma, restriction colon function, and so on. So I'm just going to make a note here. Desmos piecewise. Give your function a name, equals, and then it's always your restriction, colon, and then whatever your formula is. Comma, and then you can just keep adding those on. Restriction, colon, formula. Yes, sir?
No, I'm stretching.
You're stretching again. Okay, stretch is a good thing. So then you have, again, restriction, colon, formula. And you can do as many of those as you want. Okay, so for example, this one is f of x equals x is less than 2, colon, and I always forget that colon, throw a comma on my mistake, and I can see it screwed up, and I know I did something wrong. My formula was x squared. Then a comma, x is greater than or equal to is what I typed, to colon x plus 2 is my formula. Again, if you have more pieces, you just keep throwing in your restrictions. Okay, but I won't, on paper, I wouldn't give crazier ones than that. It's too much of a pain. So what do I want to do with that mess? So again, f of x equals x squared if x is less than 2, x plus 2 if x is greater than or equal to 2. I want the limit as x approaches 2 of f of x. So the question is, are they doing the same thing? And we can pretty much see from the graph that they both seem to be going to what? 4. It's the y value. Yeah, the limit is the result of the formulas. And both of them are heading over to y equals 4 here. Right? So the parabola as x gets close to 2. And I can check that numerically. I can say, okay, what is f of 1.9? 3.61. What is f of 1.99? 3.96, getting closer. What is f of 1.999? 3.996. And then I can look on the other side. What is f of 2.1? 4.1. F of 4.01. 2. Mental fog again. 4.01. Now they're approaching in different ways, but they're going to the same spot. Okay. F of 2.001. And if they go to the same spot, cool, we got a limit. What if they don't go to the same spot? We don't have a limit. Yeah, that's all, we don't have a limit. So I'll just give you another example of that. Let's see, sign in, remember what I did. 3 pieces, okay. So here's one I did earlier today. And what I told it to do was to graph a parabola if x was less than -2, and you can see my chunk of a parabola there, and if x was greater than -2, I said graph this line. And then I just plotted this point in the middle. That's going to be part of this function too, but I couldn't get it to graph a function and a point all on the same thing. And I'm going to snapshot this picture and just play with it for a sec. So, new page, snapshot, come on, snapshot. So here's my function, and the way I told Desmos to graph it is the parabola doesn't get to use the point, but and let's see, neither does the other function. I think it is just a greater than the other function. Yep. So a better graph of this is for me to put, switch to red, an open circle there, because the parabola doesn't get to define what happens at x equals 2. I have an open circle there. The line doesn't get to define what's happening at x equals 2. And what here I want to do is I chose the function value to be the average of those 2 y values. That's my function. So writing that up, my function looks like this. F of x equals negative x plus 2 squared plus 5 if x is less than -2. I said the function is going to be exactly equal to 3 if x equals 2, and the function was going to be 1/2 x plus 3 if x was greater than -2. So that's the piecewise function I just drew there. It's got 3 pieces, a curve, a line, and a point. So my question then for this, what is the limit as x approaches -2 of f of x? Oops, extra parenthesis there. Trash it. What do you think the answer is here? What's the limit?
There's none.
Sam says there's none, Daphne says there's none. 3. Got a 3. So here's the way we figure that out. We take a look at this curve here, this side here, and we say, what is happening as we approach -2 from the left side? What are we getting close to for y? 4. We are getting close to 4. So the limit as x approaches -2 from the left side of this function is 4. Do the same thing on the right side. Approach from the other side. So what's the limit as x approaches -2 from the right side of this function? 2. That appears to be 2. Do the left and right sides match? No. Therefore, the limit does not exist. So if it doesn't say approach from the left or the right, that means you're compelled, you're obligated to look on both sides. And if they match, you have a limit. If they don't match, you don't have a limit. So the limit does not exist. This function is broken. Does the function exist at that point? Yeah. Turns out that f of -2, so that's supposed to be a -2 there, that happens to be 3, but there is no limit because it's all broken up. Okay. And that gets to Daphne's crazy question that she asked about. Sorry, it wasn't a crazy question. The question is crazy. And I thought about not putting in the homework, but it was just so goofy I had to put it in there. And okay, so here it is. So let's see, we're asked about here f of 6. So here's x equals 6. F of 6 appears to be 4. Yeah, so it's just looking at the piecewise graph and saying, can you answer some questions about it? Okay, approach 9 from the left side. Okay, so here's 9. I'm on the left side. It is 4 again. Yeah, so just looking at the graph and looking at the approach. F of 6 from the right side. 4. Oh, interesting. And then if I try to find the limit at 9, which means I have to consider approaching from the left and the right, they don't match. There's no limit. So I would put D and E does not exist. Okay. Submit. Woo, I got them all right.
Let's say like if f is 7, and if that's a
Yeah, so if it said what's the limit at 7, we would say, well, at the left it's going to 6, on the right it's going to 6, so yeah, the limit is 6. Okay. Does the function exist at 6 though? No, there's a hole there, but the limit exists. The limit's okay. Yeah, so these are some weird edge cases that happen with limits. So we are out of time for fun with math today. I am now slightly behind schedule because I mentioned yesterday we needed to talk about asymptotes in section 2, and we haven't gotten to that. So we're going to have to continue with section 2. That means I'm going to shift the homework for 2 over to Monday night. But give it a try anyway. You'll probably figure it out based on your past experience in math. But I'll move the homework anyway. You already finished it? You're ahead of schedule. Woo! Okay. All right, have a great day. Do good math. So nice to meet you. Let's see, who's still there? Is that Connor?
I did my count.
Yeah.
Okay, thanks for joining us, Connor.
Yeah.
Have a great day. I'll see you in the future.
Yeah. Thanks.
Yep, bye-bye. Yep.